Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. In today's lecture, we are going to discuss a core topic of number theory. You can say that uh, your number theory takes its start from this definition. So, what is the divisibility? In last lectures, we have discussed about division algorithm uh, that can be defined as if you divide an integer b with a non-zero integer a, then there exists a unique quotient q such that we have a remainder r. Then you can write b is equal to a into q plus r, where your remainder r lies between 0 and b. In case, uh, in this definition of doing algorithm, your remainder r is equal to 0, then your b becomes a into q. What does this equation shows? This equation says b is exactly multiple of a. B is a multiple of a, or in other words you can say a exactly divide b. So this is the concept that we will discuss in today's definition of divisibility. Let a and b be the two integers with where a is a non-zero. Then a is said to divide b if there exists an integer c such that we can write b is equal to a times c. We can discuss this definition with a simple example. When you divide 12 by 3, then we have an integer c which is 4 here, for which remainder is 0. In other words, you can write 12 is equal to 3 into 4. But in case if you divide 11 by 3, we have remainder 2. This shows that 11 is not exactly divisible by 3. So a number b is called uh, b is divisible by a if there exists an integer c such that we can write b is equal to ac. If a divides b, then symbolically we write it as a with this vertical line b. So this symbol shows a divides b. Otherwise it is written as if a does not divide b. Not a divide b is a different from this notation, because this notation is just a fraction. For example, when we say 3 divides 12, then in this case there exists an integer c is equal to 4 such that we can write 12 is equal to 3 into 4. As here 3 divides 12, we denote it as 3 with this vertical line between 3 and 12. However, 10 is not divisible by 3 because there is a no integer c that makes the statement 10 is equal to 3 times c true. You cannot find any integer c uh, such that when we multiply that integer with 3 and it gives 10. So if a divides b, then we can also say a is divisor of b, or a is a factor of b, or you can b is a multiple of a. These are the three other alternative phrases that you can use for divisibility. Note, if a is the divisor of b, then minus a is also divisor of b, because uh, b is equal to a times c implies b can be written as minus a into minus c. This shows that divisor of an integer always occurs in a pair. To find all divisor of an integer, it is sufficient to obtain a positive divisor, then adjoin to them the corresponding negative integers. The most important thing or the key point in the definition of divisibility that you have to remember, when we say A divides B, then it can be written as B is equal to AC. So you have to remember both sides of this definition. When you write A divide B, then it is equal to B is equal to AC. Sometimes we have B is equal to AC as an equation, then it means A divides B. We will use both of the sides in the next theorem. This theorem is actually, you can say, these are the properties of divisibilities. These are the properties of divisibilities. For integers a, b, c, we have three integers. Then the following properties hold. A divides 0, where a is itself non-zero. 1 divide a divide a. This property says 0 is divisible by any non-zero integer. 1 is a divisor of any integer, and any integer is divisible by itself. The second one is a divides 1 if and only if a is equal to plus minus 1. If a divides b and c divides d, then ac divides bd. A divides b and b divides c, then a divides c. This is the transitive property of divisibility. Fifth one is if a divides b, b divides a, then a is equal to plus minus b. If a divides b and b is a non-zero integer, then absolute value of a is always less than or equal to absolute value of b. If a divides b and a divides c, then a divides bx plus cy. This property, you can say that if a divides b and a divides c, then a divides the linear combination of, here the number or the sum bx plus cy. Actually this represent linear combination of b and c for all x y belong to z. So we will prove all of these properties one by one. In the first property, we have to show if a divides 0, where a is itself non-zero. Firstly, I am writing the definition. As we know that a is called divisor of 0 if there exists a positive integer m such that uh, 0 is equal to m times a. Now you have to remember the definition from both sides that I discussed above. A divided 0 means this implies there exists an integer m such that you can write here what is here divisor. A is divisor here. A is divisor, and what is 0? 0 is dividend. So according to division algorithm, you can write dividend 0 is equal to a times m. M is an integer. So we have an equation 0 is equal to m times a. How can we get this equation? By simple the definition of divisibility. Now, you have to think that how for what value of m this definition hold. As 1 is satisfied for m is equal to 0. If you put here m is equal to 0 in 1, we can write 0 is equal to 0 into a. Now what does this equation shows? This equation shows a divides 0. This implies for all a belong to z. I again repeated that I tell you the most important thing about divisibility is when you say a divides 0, this implies 0 can be written as the 0 can be written as the multiple of a, mean to say a into m. If 0 is equal to a into m, then reversely you can write it as a divides 0. So when you say 0 is equal to 0 into a, then in the form of divisibility you can write it as a divides 0. Next, consider 1 divide a. Now we prove uh, its second part, that is 1 divide every integer a. When we say 1 divide a, then by definition 1 is called divisor of a if there exists a positive integer m such that you can write it as a is equal to m times 1, m into 1. What is dividend? Dividend is here a on the left side, and what is divisor? Divisor is 1 on the right side, and m is an integer, so you can write it as a into m into 1. Now you have to think for which value of m question number 2 hold. As 2 is satisfied for m is equal to a, so we can write a is equal to a into 1. And if you write it in if you write this equation in the form of divisibility, you can write it as 1 divides a for all a belong to z. Next, in the third part, we have to show that every integer is divisible by itself. A is called divisor of a if there exists a positive integer m such that we can write a is equal to m into a. Now we have to find m for which m this equation satisfied. As 3 is satisfied for m is equal to 1, we can write a is equal to 1 into a. And if you write this equation in the form of divisibility, you can write it as a divides a. Next, in the second part, if a divides 1, a divides 1 if and only if a is equal to plus minus 1. In other words, you can say that there are the only two possible divisor of 1, plus 1 and minus 1. Suppose a divides 1, then we show that a is equal to plus minus 1. Suppose a divides 1, this implies there exists an integer c such that uh, 1 is equal to 1. 1 mean this is my dividend. You have to remember the division algorithm. Division algorithm says dividend is equal to divisor into some quotient q plus remainder. Remainder is here 0. So this is my definition of divisibility here. My dividend is here 1, so that's why I write here 1 is equal to c. C is an integer, that is quotient, and a is divisor. So this definition become 1 is equal to c into a. Say this is my equation number 1. Now you have to see this equation 1 is satisfied for which values. This equation 1 is satisfied for which values, as 1 is satisfied for the pair when you put here a is equal to 1 and c is equal to 1. If you put here 1 is equal to 1 into 1, this equation is satisfied. And if you put a is equal to minus 1 and c is equal to minus 1, then again you can see that this equation is satisfied. This implies there are the two possible values of a for which this equation 1 is satisfied, that we have obtained by the definition of divisibility. This implies a is equal to plus minus 1. Conversely, we suppose that a is equal to plus minus 1. We show that a divides 1 as a is equal to 1 can be written as, can you write it as 1 is equal to 1 into a, because here a is 1. A is 1, this implies 1 is equal to 1 into 1. This shows that a divides 1. If you convert this equation in the form of divisibility, you can write it as a divides 1. Similarly, if a is minus 1, we can write 1 is equal to minus 1 into a, because my a is now minus 1, so minus 1 into minus 1, again 1. This shows a divides 1. In the third part, we have to show if a divides b, c divides d, then the product of divisor divides the product of dividend, that is AC divide BD. First consider A divides B. When A divides B, it implies there exists an integer m such that we can write B is equal to A into m. Similarly, when C divides D, this implies there exists an other integer n such that we can write D is equal to nc. As we have to make the form of BD, that is the product of B and D, and AC. So multiply. That's why we multiply question number 1 and 2. We have by multiply left side with left of both equation, we have BD is equal to Mn into AC. As M and N both are the integer, so their product is also an integer. You can write it as another integer. Suppose this is K. So this becomes BD is equal to K times AC. And if you write this equation in the form of divisibility, we can write it as AC divides BD for some integer K belong to Z. That completes the proof. Fourth part, that is the transitive property of divisibility. If A divides B, B divides C, then A divides C. A divides B implies there exists an integer m1 belong to Z such that we can write B is equal to m1 into A. B divides C implies there exists an integer m2 such that we can write C is equal to m2 into B. Now in the final definition, we have to show A divides C. It means we have to eliminate B from here. So we put the value of B from 1 in 2. Using 2 in 1, we have using 1 in 2. 1 in 2 here. Using 1 in 2 here. Using 1 in 2, we have C is equal to m2 into m1a. As m1 and m2 both are the integers, so their product is also an integer. Say this integer is m3, so we can write it as C is equal to m3 into a. That shows A divides C, which completes the proof. Fifth one, if A divides B and B divides A, this is possible if and only if A is equal to plus minus B. A divides B. When A divides B, there exists an integer m1 such that we can write B is equal to m1 into A. When B divides A, this implies there exists an integer m2 belong to G such that we can write A is equal to m2 into B. Using 1 and 2, we have plugging the value of B in equation number 2, we have A is equal to m1 into m2 into A. By cancelling out A from both sides, this gives m1 into m2 is equal to 1. Here 3 shows m1 and m2 are reciprocal of each other, as m1 and m2 are the integers. So this question 3 is possible only when m1 and m2 both are equal to 1 or both are equal to minus 1. Because there are the only two integers whose product is 1 and they are also reciprocal of each other. So this is possible both are 1 or both are minus 1. Case number 1, if m1 and m2 are equal to 1, then it shows if you put m1 and m2 is equal, both are equal to 1, then from either any equation 1 or 2, we have A and B are equal. And in case if m1 and m2 are equal to minus 1, then A is equal to minus B. Hence from both cases we have A is equal to plus minus B. Its converse part, I hope you can do by yourself. This is your assignment simply. Next, in the sixth part, if A divides B and B is non-zero, then we have to show that the absolute value of A is less than or equal to absolute value of B. A divides B means there exists an integer C such that we can write B is equal to A into C. As B is non-zero, so this definition hold only when C is also non-zero. as b is a multiple of a, this and b is non-zero itself, it means it must be that c must be non-zero. Upon taking absolute value, we get, taking absolute on value on both sides, we have b absolute is equal to a into c. This can be written as a absolute into c absolute, as c is non-zero. So and c is non-zero and c is okay. As c is a non-zero integer, so for any non-zero integer, its absolute value is always greater than or equal to 1. To make the form of b absolute is equal to ac, we multiply this inequality with a absolute on both sides. This gives a absolute into c absolute greater than or equal to a absolute. As a absolute is always positive, so it will not reverse the inequality. As this is equal to b absolute, this shows that b absolute is always greater than or equal to a absolute. That is required. Now we move towards the last part of the theorem, which says that if A divides B and A divides C, then A divides the linear combination of B and C. Simply by using the definition of divisibility, A divides B implies there exists an integer m1 such that we can write B is equal to m1 into A, multiply on both sides by x. Why we are multiplying with x? Because if you see here in the linear combination, b is multiplied with x, so multiply this equation with x, we have bx is equal to m1 into ax. Say this is equation number 1. Now we use the second part, that is a divides c. A divides c, it means there exists another integer m2 such that we can write c is equal to m2 into a. Again, if you see in the original statement, c is multiplied with y, so we multiply this equation with y, we have cy is equal to m2 into ay. Now lastly, this is the form of sum. So adding 1 and 2, we have adding 1 and 2, these two equations, we have bx plus cy is equal to m1 into ax plus m2 into ay. By taking a as a common multiple, we have m1x plus m2y. This shows that bx plus cy is equal to a into m1x plus m2y. As x, y, m1, m2, these are the four integers, so their sum of product is also an integer, so this also belong to z. So say this is m3, so by plugging this value or by replacing this is equal to m3, we have bx plus cy is equal to a times m3, which fulfill the definition of divisibility, which says a divides bx plus cy. So I hope now you have a clear understanding of the core topics of number theory, that is the divisibility. In the next topic, we will discuss the definition of GCD, greatest common divisor. That is also very important in the journey of number theory. So if you find my lecture helpful, kindly like, share and subscribe. See you in the next lecture. Take care. Allah Hafiz.